Okay, welcome everyone. Go back our class. I hope this class is not so boring for you because the quantum computing is very hot. So now we'll go to the understand some fundamental part for the quantum. Okay, today we will cover about the two type inner products. This is the part of introduction to the quantum computing and programming course. Okay. So we will focus on inner products and the quantum inner products. So, okay, the last lesson we already learned about the linear operator, and we learned about the unitary operator. So, but that's the only definition. So today we will learn more about how we can add two vectors by the linear operators. Yeah, okay. We have four the function or computation, the vector addition, scalar, the vector multiplication. We have a linear mapping, and we have inner products. So this is the last part, to cover in this lesson. Okay. So okay, the first we have some concept to separate two concepts. We have a traditional the inner products. Every traditional, so we have this one is this symbol. Okay, for example, this is a comma. Yeah, and but in the quantum inner products, so you will see different. Right? That is symbol to make sure in future when you see this kind of formula, you can see this kind of traditional or the quantum, and how you can transform between the two kind of version. Yeah, two kind of version. So okay, that's the first thing. And if you see over here, so this kind of you see, for example, we have that vector v is a vector space in the complex vector. Okay. And now we have a function. This one is traditional, right? Traditional inner products. So we have a function from the traditional v multiplied v, still in a complex vector. Okay. So if this kind of traditional inner products can satisfy the the new condition, so it's called the inner products. Yeah. It's, so have three conditions. The first, this one. So that means after you multiply multiply in linear operator, so you can transform this value from outside. Yeah, that you can achieve is a transform outside. And the second condition. This is traditional, okay? This is traditional, the inner products. Equal, to conjugate. This conjugate, you see this kind of formula. Conjugate, and you see this switch order. This is UV, right? And you see equal to conjugate for vector VU, okay? VU. So that is a second condition. The last one is, so the third one is if the inner products, the two vectors, this is the two itself, the vector itself. So this one is or reply one the condition. This vector equal to 0 if its the value have a 0 only. Yeah. So this is kind of traditional or inner products. Yeah, this inner products. So yeah, you see need to satisfy three the condition. Actually, this part is reminds one of important. Actually, is need to follow the linear operator, or linear combination. Yeah, and over here is give one of example of. Yeah, we have how to prove. Yeah, so okay, we have vector v and have an inner products with this vector u and this kind of linear operator, right? So after we multiply, so we can this kind of conjugate distribute the property. So we can move out. This one but we need to change to conjugate, conjugate the properties. Yeah, to conjugate the property. Actually, this kind of theory, theory, and this is how we prove. Yeah. So this one formula, I hope you remember. Yeah, remember, because this kind of theory and requires some proof. Yeah, proof. And okay, so the first concept after we have that kind of basics knowledge, we can define about the standard inner products. What is standard? So over here with standard, this kind of traditional, right? Because you see this one, you can see that kind of traditional, right? Traditional inner products, after we transform to standard inner products, so it's equal to, this kind of the linear combination. We have a U, you can see we have this one kind of, okay, U1, U2, and UN. This kind of U1, U2, and UN. Okay. Okay, this is the original. And when inner products, standard inner products, that means you need to multiply this V. Vector V is conjugate, so it's a vector V original. This V. V1, V2, Vn. So standard inner products, that means you can multiply this kind of value in the conjugate, for the second, this one, second, the element for the second vector, that is for standard inner products and in traditional way. Now we're talking about the quantum. So the quantum. So we talk about the quantum, so you will see this kind of symbol, right? Different. And we see about the same complex vector. But to make sure the function, the quantum inner products can call about quantum inner products if they need to satisfy same to three dimensions, three the requirement, 1, 2, and 3. The first one, similar like traditional, okay? When you multiply with any A vector space A, B, C, you have this kind of constant, okay? If you multiply with element in the vector, so you can move out, okay? You can move out. But inside you still this kind of quantum inner products, okay? So still keep, but we can move a constant outside. The same, the third one, second one, if we have the quantum inner quantum inner products for vector U over vector V, so we can conjugate. It's different from the standard. The previous one, we use the traditional. We have this one common, right? But this is standard in the quantum, so we have this kind of formula, and we have conjugate. Actually, it's a kind of very similar kind of how to write, but it's different meaning. And the third question, third condition, if you want to, replace itself, so the value for vector U equal to 0 if its value equal to 0, its value equal to 0 is very important. The quantum inner products only the element equal to 0 if it's the inner, the element is equal to 0, And here is the conjugate distribute property. Property quantum, okay? It's different from the, we have a conjugate distribute property for the traditional model, and we have a conjugate distribute property for the quantum part. So over here for the quantum part, But it's similar. Like we move outside, we need to calculate the conjugate, conjugate for A and B, and we need to keep, this one is element multiply with x element của U and multiply with over V. So this is how this is proof. So conjugate, so you can move, conjugate, and you can follow the conjugate formula and try to split the two parts. Okay, and this is the example for standard quantum inner products. So we have a vector U and vector V. So if we have a standard quantum inner products, so we have this one, right? So we can multiply with this, Okay, so U star equal to the kind of conjugate for vector U, and conjugate, and you can multiply with x conjugate like this. Conjugate. Okay, so if you this one is already type of right here. We have x conjugate, we multiply. So here example, we have U vector V and V. If we have this guy, we find this traditional and this quantum, right? Quantum. And this traditional. So in the traditional, so we can follow the formula, the last part. Yes, follows this part, and to calculate about this one. And you can see we have A star, and conjugate. This one is conjugate, and after you calculate this one, okay. And about the quantum, this quantum. We have this one. We have U star, right, and V, right. This is U star, and U star equal to conjugate, right? U star equal to you can conjugate. For example, conjugate for 1 plus the y equal to 1 minus y I. Okay, similar. This one conjugate. Conjugate. So after you calculate this kind of value, we have a toaster. So we can find. Okay, so the value for this one is this is minus, right, and this is plus. So we can see the traditionals. The inner product is different, the quantum inner products. But if we can conjugate the value, reverse back, so we'll see, you can see this kind of, the traditional, the vector is equal to conjugate in the quantum. Okay, that is the kind of reverse method. It's not equal to each other, but it's equal to conjugate the part. Conjugate the part. So, so this is kind of the conclusion. We have a relationship between the traditional version and the quantum version. Okay, the quantum version. So that is actually most important part. This one is we have U and V. Sorry. So this one is equal to, this one is equal to the U, V, conjugate, or actually is U, V, conjugate U, V. Okay, this one is a relationship between the two one. So you can see. Okay, that is the conclusion. Remember this part. Okay.